GIFC, workbook, physics, mechanics, lecture 14 for mechanics. Problem? Oh, probably want the screen on, huh? What? What's
written under on the screen? There's a word written.
here?
Is this English?
Yeah, it is.
Really?
Can you read it? It just says Bush. It's the name of the company. But my TV is not turning on. Come on, dudes. Oh, okay. I should be patient. Come on. Come on. It's plugged in. Oh, there we go. It's doing that black line thing. Cantilevers and further support. Got it? Yeah. It's not actually a lot to do in this one, but the questions, they can be a little bit tricky. So anyways, before we can start, we have to look at what a cantilever is. And here's the three types of cantilevers. So the first one is called a simple cantilever. This one is a braced cantilever, and this one's called a braced cantilever as well. The difference is how they're braced. So this one is braced by a compressive strut, or just a strut, and this one is braced by a tensile stay. So it's braced by a stay. In other words, this one is supported by underneath, and this one is supported from above. And this one is not supported. Now, how do we define a cantilever? So the definition isn't on the exam, don't worry. The definition is quite formal, but I want to do the definition because it will help your vocabulary. So a cantilever is a rigid, okay, so what's the word rigid firstly?
Strong.
Yeah, kind of strong, but it has another meaning as well. It is usually strong though.
Hard.
Yeah, hard or firm, yeah. Structural element. Structural element means something used in buildings. Such as a beam or a plate. These are beams. Anchored. What does anchored mean as a verb?
Placed.
Yeah, but in a very particular way. Do you?
Hooked?
Yeah, like hooked, like attached. Like fixed. At one end, at only one end, to usually a vertical support. So usually there's a vertical support from which it's protruded. So what's protruding? Coming out, sticking out, yeah. So you definitely need to draw these pictures with the words and the definition. So you need all of this slide. Now take your time because this is like the key slide for the whole lesson.
What do they mean by such as a beam or a plate?
Like as an example, like a wooden beam, which is like a plank of wood, or a plate, like a metal plate, like in other words, something rectangular usually. Is it Andy?
Yeah.
That's your preferred English name, isn't it?
Sorry?
Your preferred English name is Andy.
Actually, people call me Andy. A-N-D-E-K.
I heard no difference.
And deck.
Andek, okay. No, I thought it was Andy, and when I was looking at the attendance there, I'm like, Andek? But I've been saying Andy. No, I better check. Andek.
Yeah.
What does protruding mean?
Yeah, Siba, what's protruding? You said it earlier.
Like, coming out.
Yeah, like sticking out, coming out, yeah. Huh? How's our pictures going? You got them drawn? Just right underneath, simple, braced and braced. Yeah.
What's it? Compressive structure?
Compressive strut.
What does that mean?
A strut is like a support,
Okay.
and compressive means it's supporting by pushing, that you can kind of.
Yeah, I just didn't know.
This is the
structure.
strut. Yeah, struts. It's funny because strut is the word you give to like a piece of wood that's being used to hold something up on a wall. But usually only this way. So like you wouldn't call this leg a strut. But if I stick this leg into the wall to hold up a table that's stuck to the wall, now all of a sudden I call it a strut, you know. Okay, got that? So I have a little competition for you. The prize will say the chocolate bar. Somewhere during the day, I won't tell you where, but somewhere when you're moving around the school, going from classroom to classroom, you'll come across a very good example of a braced cantilever. It's a very obvious example of a braced cantilever. Looks made of metal. When you see it, the first one to take a picture and send it to me. Chocolate bar for you. Okay? So it's a very, very obvious one. And I think you must pass it many times every day, and perhaps you didn't even notice. So be on the lookout for it later today, okay? We'll see who spots it first. Okay, so continuing. And we'll go straight into an example. Now, I've got two examples here, but they're quite... Okay, so before we start, they're a little bit long, the students find them a little bit difficult, and they continue from the last lesson about turning force. So we're going to all do this together, we're going to take our time. So let's just read it and draw it together. So a 40 by 20 sign of mass 2 kilograms is hung by means of a braced cantilever. So the picture looks like this so far. You've got your wall, like a shop wall. You've got your braced cantilever. Now I didn't say how it's braced, so maybe it's a string or maybe it's a strut. And at the end of it I have a sign. Now, I know how big the sign is, don't I? It's 40 centimeters this way, and 20 centimeters this way, and it has a mass of 2 kilograms. And it's hung by means of a braced cantilever. The stay is attached 40 centimeters up the wall. So here to here is 40 centimeters. And the other end is attached to the end of the cantilever. So it's attached to the end here like this. Okay. And I'm sorry, my question actually isn't clear, but I think I must have meant that this sign is for the whole cantilever, although I didn't actually say that, so I'll just fix that sign up. So, you know, like a shop sign. Make it Starbucks. Okay, and it's 2 kilograms, and there's the thing here, the beam. Okay, and do I have any other info? No, that's everything. Okay, so this is the picture. Are we happy with the picture? So before we even do the questions, I'll just give you all a minute to just draw this, to copy it down, and then we'll have a look at the questions together. Got that drawn? Yeah. So let's have a look at the first question. So the first question is, what is the tension in the stay? So how much force is in the stay here? Now let me draw the forces first. So the first one I'll put in is the weight of the sign. So that would be right here in the middle, agreed? And how big is the weight of this whole sign? I said it's 2 kilograms. So downward force here is 2G. Yeah? Yeah? Now what force should I draw next? I should draw the tension here in the stay. So I'll just call that tension T. Yeah? And is there a tension at this end? What do we think? Where it's attached to the wall? There is. But which way is it? Is it pointing in or pointing out? Yeah. Now, I think we talked about this recently. Does anyone remember the reason why the tension at the other end is pointing this way and it must be the same?
There's nothing then it will turn.
Yes, or, well, it'll stretch. Yeah. So these have to be equal in the strength. But there's one more force I did not draw on my picture. And I wonder if anyone can see my missing force. Yeah, where though? Like, where should I put the missing one? Any ideas? No?
On the right side of T.
Here?
Yeah, upwards.
And what would be providing it? because it's not in contact with the ground here.
But it's getting pulled by T.
Ah, yeah, well that's all we already considered in the T.
Up in the middle upwards?
Middle upper, like here? Is it? Where? Should I go up, down, left, right? No? No one's going to tell me? No one? No one? Okay. Here, the reaction between the sign and the wall. Because think about it. It's being pushed against the wall, isn't it? Like if I have this string pulling it into the wall, why doesn't it keep moving? Because the wall pushes back. Okay? Now, I actually draw the reaction force at an angle here. Now you might say, why is it at an angle? Why is it not coming out? And this is the reason. If I go to the side here. Here I have a hinge. Do you remember this word, a hinge? Like the door hinge. And I stick something around the hinge. Okay? This hinge has two jobs. The first one is it's keeping the sign up. It's like holding it. But the second one is the wall is pushing out. Because it's preventing it going to the left. So this is a reaction to prevent left movement. And this one's holding it up. So this force, what does it do? It prevents falling. Because it's like if this is the hinge and I connect it into the hinge, this is doing two things. It's stopping this from falling, because it's holding it, and also if I push to the left, it pushes back, so it stops it moving leftwards. So because of the two, we can imagine it doing one job, which is a force at an angle here. So that's why I put it at an angle here. The hinge force is at an angle. Okay, so now that I drew in the forces, let's calculate. So we should find, before we start, some missing angles. So if I just draw a triangle here, did I got my info right? This side here is 40 centimeters. This side here is 40. So could we know this angle? We could. What is this angle? How will we get this angle?
Sine.
Yeah. Well, opposite and adjacent. Tan.
Yeah.
Tan inverse of what?
40 over 40.
Tan inverse of 40 over 40, which
45.
45 degrees. Yeah. So in other words, this angle here, that is 45 degrees because it's tan inverse 40 centimeters over 40 centimeters. Okay. Now, why do you think I care about getting this angle? Why do I care about this one?
It's going to help us find out.
Yeah. So, just before I continue, I'm going to delete something. I'm going to delete this here from my picture. And the reason I'm deleting this is because I only want to focus on what's happening to the beam. So when I look at the picture of the beam, I don't care about what's happening up here somewhere else. I only care about what's happening to the beam, this thing here. So how many forces are on this guy? 3 forces, isn't it? I am going to resolve this horizontally. So this will be a force this way, and this will be a force this way. How big is this one? If this angle is 45, what's this side?
T cos 45.
T cos 45. And this one?
T sine 45.
T sine 45. Right, let's see what equations we can make. I'm sorry, I should perhaps use a different colour. Can you see this one here? That's purple there. And purple there. Purple. And purple. Okay. So, the up force equals the down force because it's in equilibrium. So what's the up force here? How big is that? It's this one Yeah, and then it's the vertical part here. And then the left one equals the right one, so you could say the left force here equals the right force here. But the most useful one is the turning force. So what I'll do is I'll look at the turning force around the hinge. So the hinge being this thing here. Okay? So if this is the turning point, tell me, is this force this one here, clockwise or anti-clockwise? This one here. Clockwise, yeah. This up one here? Anti-clockwise, because it's making a turn around this way. And lastly, this guy here? Nothing, yeah, why?
Because it's at the table.
Yeah, give me a sentence. Why do I not care about this one?
It passes through the...
Yeah, this one passes and points directly to the hinge. So it doesn't make a turn. Alright, so let's start with the first one. What's the distance from the hinge to this point? Here to here, what's that? What's the distance? 20 centimeters. And what's the force? 2G. This one here. Yeah? Now, that should equal the anti-clockwise. So what's the distance from here to here? 40. And the force? Yeah, so what would it be? T?
T sine 45.
Can you see? T sine 45. It's this one here. Yeah? Can I get the T? Of course I can, because all I have to do now is, yeah, divide by 0.4 and also divide by sine 45. And now I've figured out what the T is, which was my first question. What's the tension? So the trick is to calculate the turning force using the hinge as the turning point. That's how we got the tension in the string. You see, this is not a lot of maths, it's a lot of thinking, okay? So I'll pause and let you write this much down, and then when you're ready you can tell me what the T was. About 14 newtons, is it? 14.4 newtons is my guess. You've got it there?
I think I got it.
What you got?
6.94.
I was way off. 6 point...
994.
shall I trust you?
No.
6.94 newtons, you reckon? 2G is about 20. The fifth 20 is about 4.
13.87.
Actually, that's what I was thinking. It was around 14. Sorry. 13.87. Questions? Will we do the next part of it? Next part. What's the horizontal reaction? Okay, so if I just zoom in here. Whoa.
Oh yeah, I got it.
Okay. This has two parts. There's a horizontal and a vertical. Yeah? Now the only problem is I do not know this angle. So I can't say or cosine or sine, because I don't know the angle, okay? So what I'll do is I'll just call this part x and this one y. That's all I can do. And my question is, what is the x? Okay, so let's look at getting the x. So I can say the force to the right, which is x, should equal the force to the left. And what is the force to the left in this picture? What force is pointing left in this picture? T cos 45, yeah. Now, do we know T? We do. And do we know cos 45? Of course we do. So can we get x? Of course we can. So what's that? About 9 newtons about?
9.8.
Not too bad. 9.8 newtons then. Now, I'm willing to bet part C is I probably asked you for the y. Let's check. Yeah. So, if I go back to my picture, the up force y, well actually, how many up forces are there altogether in the picture? How many forces are pointing up in this picture? Two. What are they?
Y and A.
Y and, well, yeah, sorry, what you call the A, the T sine 45. And what about the down forces? 2G. So, we can say Y plus T sine 45 equals 2G. So that means Y equals 2G minus T, which is 13.87 sine 45. Sorry, my handwriting's a bit messy there. That's a plus T sine 45. What's that, about 11.2 or something?
9.81.
9.81, alright. 9.81 newtons then. Okay. D. What is the magnitude of the reaction force? So, we've just worked out, if we look at the wall, there's an X force this way of 9.8 newtons, and there's a Y force this way of 9.8. I guess this must have been 9.81 as well. 9.81 newtons. So my question is, what is this force here? Now, how can I get this force? This magnitude, this total force here. I think somebody knows how to get me the or. Yeah, what's the formula?
9.81 squared plus 9.81 squared and square root.
Yeah, square root 9.81 squared plus 9.81 squared. That's how I can get the magnitude of the two together. What is it?
13.87.
13.87, so 13.9 newtons. And lastly, E, I'm sure I probably asked for what is this angle. So how can I get this theta here? Tan inverse what? Over what? For this angle here. Yeah. Yep. And what numbers would that be in this picture here?
45.
Yeah, well what numbers do I put into my fraction?
9.81.
Yeah.
9.81.
Yeah. Okay, you seem very confused. I don't know if you're tired, if you're sick, if you're just confused. A little bit of everything's tough. Okay.
Can I just take a look at the diagram?
My beautiful picture. Yeah. It's terrible now because there's so much drawn on it at this point. You can ask me.
No.
Continue?
I just thought I was missing something.
Continue? Yeah? Okay. Right. Next one. A 13 kilogram ladder of length 13 meters is up against a wall, and its foot is 5 meters from the foot of the wall. So you've got a wall here, ground here, ladder here, and this ladder is 13 kilograms, and it's 13 meters long. Yeah. And this distance here, I tell you, is 5 meters. The wall is smooth. This is smooth. And down here, this is rough. What is the angle of the reaction force at the foot of the ladder? Okay, so let's begin by drawing in the forces. So what force will I put in first? How about I put in the weight first of the ladder? So, how big is this force here? 13 G. Okay. Now this is a bit like the cantilever. There's a reaction here. But which direction does it point, the reaction here? Up, down, left, right, or at an angle, or what?
Down smooth.
So like here? Is that what you're thinking?
Because if that was rough, if that floor was rough as well, smooth, it would slip.
Yeah, okay. So you're right in thinking the smooth affects the direction here. Well, firstly, let's figure out, is there a reaction to the right? What do we think? Oh, there is, because think about it. If there wasn't, this would just move through the wall. What's the wall doing? It's pushing back, because the ladder is pushing in. So, are we happy that we understand that there's a force to the right? Okay. Is there a force holding the ladder up? No, because it's smooth. Think about this. This wall, imagine it's ice. This is ice. It's nice and smooth. Okay, it's slippy. If I put my hand here, this wall is actually kind of smooth, soft. So if I put my hand here, I'll start slipping down. Okay, but if I have a rough wall, like I don't know, where the heck's the rough one? It's a bit too high up. Maybe down here. Oh, that's kind of smooth as well. And it's not able to keep me supported up. Okay, so there's no ability to keep the ladder held up. All it's doing is stopping me falling into the wall. Because if I lean into the wall will push out. But it's not holding me up. Okay, so we only have a force out here, which I'll call it S. Now what about at the foot of the ladder? What's happening there? What do we think? So again, imagine that the ground was ice. What would happen to the ladder?
Upward force.
No, first there is an upward force, true. But first, let's put the upward force in. So there's an upward force here. Yeah? I'll call that guy Y. Now, what about in the horizontal direction? Is there anything happening?
To the left.
To the left, very good. Now, why is it to the left? What does imagine this was ice.
It wouldn't be to the left, it's going to be slippery.
Yeah, well, let's think. If this was ice, what would the ladder do if it was ice? If there was no force, it was ice. what would happen to this ladder?
Fall.
It would fall. Which way would it move here at the foot? Would it move left or to the right? Right. So to stop it moving to the right, there must be a force moving it to the left, which is the friction force. Okay, very good. So we have our two forces here, and we'll call this guy X. Alright. Are we okay with the picture? Maybe this picture is a little bit easier than the last picture? Yeah? So first, just draw this for me and then we'll continue. Okay, you got that? So, yes or no? We have this drawn? Okay. So tell me, what forces are pointing up in this picture?
What?
Yeah, and that should equal what force? What's
AIB upon them.
okay, that's very dramatic.
I didn't.
You can leave because we'll be here for an hour. Are you late or on time?
Late.
How late?
10 minutes.
Good luck. Alright, the up force, what should that equal?
13 G.
Very good, 13 G. Okay. Now, what's the left force here?
X.
X. And what should that equal?
X.
X, very good, okay. So there's one more consideration. What's that? So I've done up, down, left, right. What's next? Oh no, we did down. We did up, down, left and right.
Angle.
Huh?
The ladder's angle. 2R.
2R. 2. Oh no, I mean which force should I? There's still a force situation to consider. Come on, guys, we've been doing it for 2 hours now. It's the turning force. Yeah. So we have to say the clockwise turning force equals anti-clockwise. Okay? Still with me? So my next question, which actually is an important question, is where should we place the turning point? Now, it really matters here because you can make it much easier if you pick a good spot for the turning point.
That one.
Which one is that exactly?
The point at Y and X.
Yeah, why?
Because it can fall.
Okay, so you're thinking of it, this is where it's actually turning. Yeah. Now that's fine. It is this point, and the reason is, if I use this point, I cancel X and Y, because they pass through the turning point, I don't need to consider them. Yeah? Okay. Now, let's look at this force. Is it clockwise or is it anti-clockwise? It is anti-clockwise, actually, because it's going around the turning point this way. That's anti-clockwise. Yeah. Okay. So that's fine. So this one here is an anti, and this guy up here, clockwise. Okay. Now, let's see. What part but
No, I'm trying to understand.
you don't seem that confused. What part's confusing you?
The turning point?
Yeah, everybody gets confused with the turning one. So, are you happy or unhappy that this is anti-clockwise?
Half.
And you're happy or unhappy that this is clockwise? Okay. So, we need to say that this anti-clockwise equals this clockwise. Okay. So, it's the force times the distance. Now, there's the force. Now, you have two ways to deal with this. Because this one is at an angle. So you can either change this one into a y and an x, which is a little bit messy in this particular case. Or, what you can do is say it's the force times the distance, and it's not this distance, it's this distance. Now, why is it this distance and not this distance? What's the reason? Do you remember? So it's force by distance, but it's actually not this distance, it's this distance. Does anyone remember why?
This is from the.
Well, they're both from the turning point.
I don't get the question.
Oh yeah. What's the formula for turning force? It's force by distance. Okay? So what is the force here in this picture? 13g. What's the distance to the force from the turning point? Is it this one or it's this one?
The down one?
Yeah, why?
Because they're going opposite direction, and it's the distance between them.
I'm missing a key word. One word I was hoping you would say. Why do I choose the down one and not the up one for the distance? Anyone remember? I'll tell you. It's the perpendicular distance. Yeah, so the distance line must be a perpendicular. Okay. How big is the ground? It's 5 meters. This will be in the middle because it's the center of gravity. So the distance is 2.5. Okay, and that should equal, what's the force here? Now, what's the distance? Is it this? No. Why not? It's not perpendicular. So what is the distance? It's actually this. Because if you imagine this drawn outwards more, it's that distance there.
You have to find the.
So you have to find the height. Now, how can we find the height? Well, how big is this side? 5. And how long is the ladder? 13, I said. So using Pythagoras, this side here, you can work it out as a 12. So it's s times 12. So I know my s now. 13 times 9.81. 13 times 9.81 times 2.5 over 12. So I got my s.
26.5.
26.5 newtons. Now look, because I know my s, I now know my x, because they're the same. So that's also 26.5 newtons. And by the way, Steve, since you have the calculator there, what is 13g? If you never worked that out, 13 times 9.81. 127.5 newtons. So my question is, what is the angle here? So you have an x, you have a y, you have a force here, and I want this angle. So how do I get this angle theta? What is it equal to? Tan inverse of y over x. And what's the y? Yeah, 127.5, and the x is 26.5. And now I'm finished. I have my angle that the force is at, which is what I asked you for. .25 degrees is what angle this reaction force is at with the x and the y. Now, again, there is not a lot of maths here. There's 1, 2, 3, 4, 5 lines. You know, it's not an awful lot. It was 78 point, what was it? 25. So 3 degrees then. you write this down? Yeah, Kim, you have this? Question. Is all the homework done, or what's the story with the homework?
Everything except focus.
Except projectiles.
Well, I
And for you, George?
Not much.
Not much done or not much left?
Just because of the presentation, not much done.
Ah. How many lessons of homework do you think you need to catch up on?
Like one in total when you combine all of them.
Oh, I see. If you...
So like some are done, some aren't.
Okay. Siva, how?
projectiles and like I remember a couple of questions from each lesson, like one
Kim?
each
Projectiles and... Wait and drag.
Yeah, wait and drag.
Yeah. Antek?
Still working on it, but I didn't do much because of the presentation.
Yeah, you're making your teacher feel worried. Your teacher is worried and concerned. I don't know. I don't know. Tell me, is there, what's the main problem with getting the physics homework done? Is it a lack of time? Is it a lack of understanding? I mean, what's the barriers to the progress here?
With projectiles, lack of understanding.
Okay, fair enough, yeah, okay. So that's for the projectiles then. Other people's opinions?
It's both time and like time was only this week. Like if we didn't have a presentation this week, I'm pretty sure I would have got it done. And yeah, understanding as well.
Okay. Because a little part inside of me is saying to give you some time to get your homework done, because I want to do the next lesson, but the next lesson is more of this stuff, and you're not really giving me the energy that I feel like you're understanding this and everything is going okay. So I mean, I can go on to the next lesson, or I can give you time to try and catch up on your homework. I don't know what you need right now. What are your thoughts?
I want time to try to
You want to get a handle on this stuff?
Yeah.
The turning forces. I think that's okay, because remember I said there's two things that students find most difficult in semester one: projectiles and turning forces. So I'm okay if you need more time to be working on this stuff and the projectiles. Also, you were looking for rooms for lunchtime, weren't you?
Mm-hmm.
So I have it here, I can
Can
tell
I
you.
just stay here or?
Well, I don't know, what day is it today? Thursday, isn't it? Yeah, you could, yeah.
I think we can present the book.
Oh, you need to get ready for your presentation? Ah, okay. So you won't be doing physics then? That's not why you wanted the room.
Actually we're talking about electricity.
I know. Alright. Okay. I am going to sit down with you guys and help you with these. I think this is what will best serve you. So you can start on this, alright, or you can start on your last homework you have to do. Either way, I want to sit down beside each of you now and just have a look at how your homework is going. Kim, you look very worried. No, if you're having trouble, it's not going to make me angry. I just want to see how you're doing and how I can help you. You guys seem very, I don't know, what's wrong with you?